Right, we're now going to do some examples and just focus on constant coefficient linear homogeneous equations that have complex roots. So going back to the original situation, we have a constant coefficient linear equation. So A, B, and C are all constants. It's homogeneous because there's a zero there. There's no explicit mention of time. And now we're going to, at this point, we be able to solve for all three cases. So for example, suppose that we have y double prime plus y prime plus y is 0. It's constant coefficient. A is 1, B is 1, C is 1. It's homogeneous. It's linear. So now we make the assumption that y is an exponential function. So r(e) to the nt. I can take derivatives. And so far, this is exactly like what we've seen before. Plug the derivatives into the original equation. So y double prime plus y prime plus y is 0. And we notice that every term has r(e) to the nt, so I can factor that out. And what is left is I get n squared plus n plus 1. And I don't want that to be 0. If that was 0, then y equals 0. And that's not going to be a valid solution, or at least not a useful solution. So now I don't immediately see how to factor that, so I'm going to use the quadratic equation. So minus b plus or minus the square root of b squared minus 4a times c all over 2a. Let's clean that up. So I get 1 minus 4 inside the square root. If I break this up into two pieces, because that's a negative in there, I can write this as 1/2 I times square root of 3. So my roots to the equation, I haven't said this, but this is called the characteristic equation, or the roots of the characteristic equation. I've got two parts. I've got the real part, and I've got the imaginary part. In this case, the imaginary part is 1/2 times square root of 3, and the real part is minus 1/2. Just from that alone, you should recognize we're going to have oscillations because the imaginary part is not 0. The amplitude is going to decay like e to the minus 1/2 t. And my omega then for the oscillations is going to be this. So my period is going to satisfy that relationship, and I can figure out the period of the oscillations from here. I can also now find the solution. So what do we have? We had y double prime plus y prime plus y is 0. Our roots are minus 1/2 plus or minus I times 1/2 square root of 3. So this means that our solution then I've got the exponential for the first root and the exponential for the second root. And this is going to follow exactly like what we saw previously, in that I can multiply through by the t. Oops, and I forgot the I. So let's be careful about that. This I should be here. So this becomes an I t. I got plus r2 e to the minus 1/2 t plus I square root of 3 over 2 t. This would be a plus and a minus, so this should be a plus and this should be a minus. I can break these up into two pieces. And note, this term and this term are common in both expressions. So I can factor out an e to the minus 1/2 t. And inside now I've got the r1 e to the I square root of 3t over 2 plus r2 e to the minus I square root of 3 over 2t. And I'm not going to go through all the details, but again, just like what we saw last time, is I can now write this. On the outside I have e to the minus 1/2 t. I'm going to have k1 cosine square root of 3 over 2t plus k2 sine of square root of 3 over 2t. And again, this gives me exponential decay, and this gives me oscillations, where now the period is going to be 2 pi divided by the omega, which is this term. And I can simplify that to 4 pi over square root of 3. Okay. So at this point, if you're given ax double prime plus bx prime plus cx equals 0, a, b, and c are constants, and it's homogeneous. We have the first case of distinct roots. You can deal with that. You can just take the combination of the exponentials. We can have the case of repeated roots, and now you know you take the one and then take the second, multiply by t. And we now have complex roots. So we can deal with all three cases now. Oops. So we had d plus omega I, and n2 is d minus omega I. And we know the solution is going to look like k1 cosine omega t plus k2 sine omega t. And again, just by looking at the real parts, you know that how the amplitude is going to change, and looking at the imaginary part, you know how it's going to oscillate. So let's do another example. So in this example, I've got 2y double prime plus y prime plus 3y is 0. It's constant coefficient. It's homogeneous. It's linear. So I assume a general exponential form. And I take the first two derivatives, plug that in, and I'm going to get 2 times the second derivative plus 1 times the first derivative plus 3 times the function, and that's just plugging straight into here. I'm going to factor out the exponential function, and I'm left with 2n squared plus n plus 3. I don't immediately see how to factor that, so I'm just going to let the quadratic equation do my work for me. So b is b is 1, so minus b plus or minus 1 squared minus 4 times 2 times 3 all over 2 times a. And I clean this up. So 4 times 2 is 8 times 3 is 24. So I get square root of 1 minus 24. In the denominator I have 2 times 2. So that I get minus 23 under the square root. And I can factor out that minus 1, which gives me an I. So my two parts for the real part, I have minus 1/4. For the imaginary part, I have square root of 23 over 4. So again, I immediately see I'm going to have exponential decay. The amplitude is going to decay like e to the minus t over 4. And I'm going to see oscillations because the imaginary part is not 0. So that's my omega. And I know that that times the period is going to give me 2 pi. Okay, so for the solution to this thing, what do we have? We have, Again, our differential equation was 2y double prime plus y prime plus 3y is 0. I assumed an exponential form, and I got n1 is equal to minus 1/4 plus square root of 23 over 4i. N2 was minus 1/4 minus square root of 23 over 4i. So my solution is going to be e to the minus 1/4 t. Sorry, this is a mess. This comes from this real part, all times. And then for the imaginary part, I'm going to get cosine square root of 23 over 4t plus something times sine of omega, which is square root of 23 over 4t. All right, so I get decay. I'm going to get oscillations, and my period then is going to be 2 pi divided by square root of 23 over 4. Okay, another example. So in this example, we have 2y double prime plus y prime. Oops, sorry, that was the previous example. I meant to say y double prime plus 6y prime plus 13y is 0. It's constant coefficient, it's linear, it's homogeneous. So I'm going to assume a solution like this. So my y prime is going to be the same thing times n. Second derivative is going to be the same thing times n squared. Plug this into the original equation. So I have y double prime plus 6y prime plus 13y is 0. And I have this term is in every part, so I can factor that out. It's going to be left with an n squared plus 6n plus 13. Again, I can't factor that immediately. So let's do this. I'm going to just use the quadratic equation. So minus b, which is minus 6, plus or minus 6 squared minus 4 times 13 times 1, because there's a 1 in front of the n squared. A is 1, so all over 2. So we get minus 6 plus or minus 36. Was that minus 52? All over 2. So we get minus 6 plus or minus. This is going to be, what, 16? So minus 16, is that correct? Yes. Over 2. So I'm going to get minus 3 plus or minus 1/2 square root of minus 16. Or minus 3 plus or minus 4 over 2i, which I can simplify down to 2i. So I immediately get now my solution is going to be e to the minus 3t times k1 cosine of 2t plus k2 sine of 2t. And you should immediately recognize you have oscillations that decay, and the period is going to be pi. Okay, another example. Okay, let's look at one last example. The fourth derivative of y minus 8y prime is 0. So it's constant coefficient, it's linear, and it's homogeneous, so I'm going to assume a general exponential function. I'm going to take the up to the fourth derivative, plug into the equation, see what that implies. So the first derivative is re to the nt times n. Second derivative is re to the nt n squared. Third derivative is re to the nt n cubed. And the fourth derivative is re to the nt into the fourth. Plug that into the original equation. I get the fourth derivative, re to the nt into the fourth, minus 8 times y prime, so re to the nt n is 0. Every term has an r times e to the nt, so I can factor that out, leaving me with into the fourth minus 8n. Don't want that to be 0 because That's my original equation. So that implies that n fourth minus 8n has to be 0. And I can factor out an n. And I should be a little careful here. Because I have a fourth derivative, I'm going to need 4 solutions. So when I get down to here, I already know I need 4 solutions. Well, one way this could be 0 if n equals 0. The other way is if n cubed minus 8 is 0. That's obviously one solution. Here, because I've got a cubed here, I need 3 solutions out of this. And we no longer are bound to just worried about real solutions. So there's going to be more than just n equals 2 as a solution for that. So the question now is, how do I do that? All right, well, here's the thing. This says n cubed equals 8. What do I mean by 8? Be careful. If I go to the imaginary, working with complex numbers, what does 8 mean? So we're in a math class, so 8 doesn't necessarily just mean 8 anymore. This has to be complicated. Well, one way to think about 8 is it's a distance of 8 from the origin and an angle of 0 away from the real axis. Another way to think about this is I go a distance away 8 and I do a full revolution around, or 2 pi radians. Finally, I could do 1 revolution, 2 revolutions, and go a distance 8 out and take 2 revolutions or 4 pi radians around. Okay. So what does that mean then? So where are we? We started off with saying n cubed equals 8. I'm now talking about complex numbers. And if we call this z cubed instead, I am looking for a number in the complex plane that's some distance r from the origin and some angle away from the positive real axis. And I know that when I cube that number, I got to get 8. But I can write that number in Euler form. And if I cube that, I get r cubed e to the I 3 theta. Okay? And so here's the thing. I've got r cubed e to the I 3 theta. And in terms of this number 8, I can think of this as 8 e to the I 0, no revolutions. I can think about it as 1 revolution around, or I can think about it as 2 revolutions around. At the end of this, I'm going to come back and ask, why did I stop there and not go 3 revolutions? And what we're going to find out is these roots are going to start repeating themselves. So a little foreshadowing there. But for now, I have z cubed is r cubed e to the I 3 theta. It's going to be 8 e to the I 0, or 8 e to the I 2 pi, or 8 e to the I 4 pi. And the way I'm going to set these two numbers to be equal is that the distance in each case has to be the same. And in each case, this angle has to match up. All right, so I'm going to have 3 equations, or 3 situations. In each situation, r cubed is 8. And in each situation, 3 theta is equal to this angle there. So in order for this number to be equal to any of these, the distance has to be the same and the angle has to be the same. So what are those cases? So I have r cubed e to the I 3 theta is equal to 8 e to the I 0. So r cubed is 8, and by definition, r is a real number. And by convention, we try to go with positive numbers, so r is 2. And now these numbers have to match. These exponents have to match. So the exponent on the left is 3 theta, exponent on the right is 0, so theta equals 0. So my Z1, which is r e to the I theta, is going to be 2 e to the I 0. The other situation is r cubed e to the I 3 theta. It's going to be 8 e to the I 2 pi, so that's one revolution around to get 8. Again, the distances have to match. So the distance on the left is r cubed, distance on the right is 8. And by convention, that's a real number. And now the angles have to match. So that angle, 3 theta, has to be equal to 2 pi. So now my angle is 2 pi over 3. So this says that Z2 is going to be 2 e to the I 2 pi over 3. In my third case, my Z cubed is exactly the same thing, but now I'm going to write 8 as 2 revolutions around. My distances have to be the same. So notice in each case, r is always the same. What's changing here is these angles. So 3 theta now is 4 pi. So theta is 4 pi over 3. Okay. So I have Z1 is 2, Z2 is 2 e to the I 2 pi over 3, and Z3 is 2 e to the I 4 pi over 3. Now, again, a common question here is why did I not say that this number is 3 whole revolutions around? But notice if I do that, I set those angles equal, this angle puts me back in the same place as Z1. And if I had gone 4 revolutions, this angle right here puts me in exactly the same place as that angle there. And so basically what happens is if I go 3, 4, 5, 6 revolutions, I'm going to end up repeating these numbers. So what do I have? I now have solutions for my differential equation. So I started off with the fourth derivative of y minus y prime is 0. I assumed an exponential function, and I got solutions of 0, 2, 2 e to the I 2 pi over 3, and 2 e to the I 4 pi over 3. Okay, that's easy to deal with. That's just going to be r1 e to the 0t is r1. That, again, no problem. That's just r2 e to the 2t. Notice this is going to be a constant. This is going to grow exponentially. But now I've got to deal with these two things. So this is my N1, N2, N3, N4. For N3, I have 2 e to the I 2 pi over 3. This is going to be 2 cosine 2 pi over 3 plus I sine of 2 pi over 3. What is that? So 2 pi over 3 is going to be in the second quadrant. And what is that? That's going to be, so this is my N3. It's going to be 2 cosine of 2 pi over 3 is minus 1/2. And then sine of 2 pi over 3 is going to be positive square root of 3 over 2. Yep. Okay. So this becomes minus 1 plus I square root of 3. And now for N4, have 2e to the I 4 pi over 3. This is going to be in the third quadrant. And the reference angle is now going to be pi over 3. This is going to be 2 cosine of 4 pi over 3 plus I sine of 4 pi over 3. So N3 is going to be 2 times. So cosine of 4 pi over 3 is minus 1. I sine of 4 pi over 3 is going to be minus I square root of 3 over 2. Multiplying the, this should be 1/2. Multiplying the 2 through, I'm going to get minus 1 minus I square root of 3. So for my roots, again, there's my differential equation. I had roots of 0, 2, and now I have minus 1 plus I square root of 3 and minus 1 minus I square root of 3. The real part is minus 1, so that's going to give me an e to the minus t for both of these. And notice these are complex conjugates. I've got an I and a minus I square root of 3. So that's going to be my oscillations. All right, so my omega then is going to be square root of 3. So for my solution, I'm going to get, from here, we saw that's R1. From here, I'm going to get R2 e to the 2t. These two are complex conjugates. So I'm going to get e to the minus t times cosine of square root of 3t, times a constant. So we'll call that k1, plus sine of square root of 3t times k2. So nothing happens to the constant. This grows like e to the 2t. The amplitude here is going to decay, and I'm going to see oscillations where my period is 2 pi over square root of 3. In the long run, however, this is going to go to 0 and essentially can be ignored compared to that. So my dominant term is e to the 2t. So I expect to see exponential growth like e to the 2t.